Okay, so let's talk about Wall Maria. We're talking 50 meters high, stretching for hundreds of kilometers. In the anime, it was what stood between humanity and, well, giant monsters. But let's pull this out of the world of fiction for a second and drop it right into our world. Right. If this project landed on an engineer's desk today, what would they say? Could we actually build it? So what we're going to do is treat this like a real mega project proposal. We're going to run it through a modern engineering reality check and break it down trial by trial to see what it would really take. So the first big problem for any massive structure like this, it's not some monster trying to knock it down. Nope, it's the structure itself. It's the relentless, crushing force of its own colossal weight. Engineers have a name for this, the dead load. It's just the constant, static force of the thing simply existing. And for Wall Maria, we're talking about an unbelievable amount of mass, a literal mountain range made by people. And that brings us to a really key concept, compressive stress. Basically, you take all that force from the wall's weight and divide it by the area of its base. If that pressure is too high for the material at the bottom, it would literally get crushed into powder, and the whole thing would just sink. And you know what's a perfect real-world comparison? A gravity dam. These things are enormous, and they're designed with this exact problem in mind. Yeah, they hold back water, but their number one job is just holding up their own incredible weight. And this is where we find the solution. To handle that dead load, Wall Maria can't just be a straight vertical slab. It has to be shaped like one of those dams, with a really wide, triangular base. That shape spreads all that weight out, reducing the pressure at the bottom to a level that won't pulverize the foundation. All right, so we've got the shape of the wall figured out. Awesome. But here's the thing. A structure is only as strong as the ground it's sitting on. And that brings us to our second, maybe even bigger, trial, the Earth itself. I love this quote because it just cuts right to the chase. You can design the most amazing, strongest structure in history, but if you build it on bad ground, you've just built a very, very expensive disaster waiting to happen. So let's break this down. If you hit the jackpot and you're building on solid bedrock, you're golden. It's strong, it's stable, it can handle almost anything you throw at it. But if you're stuck with something like clay, you are in for a world of hurt. A wall that big would just sink or fall right over. So how do you fix that? Well, the amount of work you'd have to do before you even lay the first stone is just insane. First, you'd have to clear away all the topsoil. Then you'd have to excavate a massive trench for kilometers all the way down to solid ground. Then you'd pour a giant foundation and anchor it with deep pilings. All of that just to get ready to start building. Okay, let's recap. We've got a stable shape, we've got a solid foundation. Now the wall has to actually face the outside world. This is the third trial, dealing with all the sideways forces, from something as normal as wind to, a giant armored titan running at full speed. Engineers have a term for this. They call them lateral loads. It's basically any force that pushes on the side of a structure. And the constant force of the wind on a surface that huge is a massive lateral load. Then, of course, you've got the whole Titan impact problem. And to put the wind part in perspective, a 100-mile-per-hour wind pushes with over 25 pounds of force on every single square foot. Now imagine that force, pushing constantly on every single square foot of a 50-meter-high wall that goes on for miles and miles. It is a relentless, staggering amount of pressure. And this is why what you build it out of is so important. Old-school masonry, like stone, is great when you're squishing it. That's compression. But the second you try to pull it or bend it, what engineers call tension, it just fails. It cracks. That's why we need modern, steel-reinforced concrete. The concrete handles the squishing, and the steel bars inside handle the pulling. It's strong against both. But here's a fascinating catch. Not all concrete is the same. See, this graph shows that you can make super high-strength concrete that can handle way more stress. But there's a trade-off. The stronger it gets, the more brittle it becomes. It can't bend or flex as much before it just shatters. So you have to engineer it very, very carefully. You might think that building a huge structure on shaky ground is a modern headache, right? Well, it's not. To find a solution, we can actually look back thousands of years. Turns out, the builders of the massive ziggurats in ancient Mesopotamia were dealing with the exact same problem: how to build these giant structures out of earth without them falling apart. And their solution was brilliant: reinforcement. And check this out. This shows you just how powerful that ancient idea is.
On the left, this model has a safety factor below 1. That means it's unstable, it's going to collapse. But on the right, just by adding reinforcement, the safety factor jumps to over 1. Now it's stable, it's safe. They were basically making composite materials thousands of years ago, the same idea behind steel-reinforced concrete.
All right, so we've looked at the wall's insane weight, the ground underneath it, and the forces pushing against it. We've even looked back thousands of years for answers. So let's put it all together. What is the final blueprint for building a real Wall Maria?
So the actual recipe for building this thing really boils down to 4 huge steps. First, the foundation. You dig down to bedrock to create a solid anchor. Second, the shape. You make it triangular to handle its own weight. Third, materials. You use modern, high-strength, reinforced concrete. And finally, you face the biggest challenge of all, the logistics.
And just to give you an idea of the sheer scale we're talking about, the Three Gorges Dam, one of the biggest construction projects in human history, used about 37 million cubic yards of concrete. A conservative guess for Wall Maria? You'd need more than 2 billion cubic yards of concrete. That's not just a big project. That's a huge chunk of the entire planet's yearly concrete production.
So what's the bottom line? Could we actually build Wall Maria? And the answer, from a pure engineering standpoint, is yes, we could. The physics checks out, we know how to do it. The real challenge isn't the science, it's the unbelievable cost and the global effort it would take to get the resources.
And that really leaves us with one last big question. We know the engineering is possible, but in the real world, could any country, or even the whole world, ever truly afford to pay the price for absolute safety?